Welcome back, focused learners. In today's explainer, we are tackling a massive piece of AI news that's going to make a whole lot of developers very, very happy. We're looking at a major breakthrough straight from OpenAI, their newly released open-source privacy filter. Honestly, if you deal with sensitive data, document ingestion, or fine-tuning workflows, this tool is going to fundamentally change how you handle data sanitization. So, before we get into the heavy tech, let's talk about the real dilemma here. How you actually scrub personally identifiable information, PII, without your data ever leaving the building. If you've built a RAG pipeline, you know this developer's nightmare all too well. You have all this unstructured text, and before it hits a vector database or some external API, you absolutely have to sanitize it. Because the second sensitive data leaves your secure environment, bam, it becomes a massive compliance liability.
Okay, let's dive into this. Historically, we've kind of been stuck with two legacy options. First up, you've got standard regex. It's fast, sure, but it is incredibly brittle and naive. Then, on the flip side, we have external APIs. These are highly accurate and context-aware, but they're slow, and crucially, they force you to expose your raw data outside your environment just to get it scrubbed. What we've really needed is a Goldilocks solution, something local, fast, and smart.
So, here is our agenda for the explainer. 1. Meet the privacy filter. 2. Under-the-hood architecture. 3. 8 detection categories. 4. Running and fine-tuning. And 5. Limitations and risks. Let's jump right in. Section 1. Meet OpenAI Privacy Filter, the local powerhouse. This right here is that Goldilocks solution we just talked about. It's a local, machine learning-based model designed specifically for high-throughput data sanitization. It sits perfectly in that sweet spot between the fragility of regex and the data exposure risks of an external API. And the best part? Because it's Apache 2.0 licensed, you can drop it directly into your commercial products without a second thought.
What makes it a true local powerhouse is its footprint. The model is 1.5 billion parameters in total, but, and this is key, it only uses 50 million active parameters during inference. This is thanks to a highly efficient, sparse mixture of experts architecture. The impact of this is huge. It is literally small enough to run entirely on a standard laptop or even locally right inside a web browser. Your data never has to be sent anywhere.
And this brilliantly illustrates the sheer scale we are dealing with. A 128,000 token context window. If you've ever tried to scrub a massive document, you know the drill. You usually have to chunk it up into smaller pieces, which inevitably breaks the context and causes errors. But with a 128K window, you can process incredibly long documents with high throughput and absolutely zero chunking. Section 2. Under-the-hood architecture. Now, this isn't just some basic script, it's a serious infrastructure-level tool. It actually started out as a pre-trained autoregressive model, very similar in architecture to OpenAI's open-weight model, GPT-OS. But they didn't stop there. They took that foundation and completely converted it into a bidirectional token classifier. So why the conversion? Speed. Plain and simple. Autoregressive models, like what powers ChatGPT, generate outputs token by token. That's fantastic for chatting, but it's terrible for fast, bulk data processing. By swapping the language modeling head for a token classification head, this bidirectional model makes every single one of its redaction decisions in one single forward pass over the input. This design choice vastly improves the speed when you're chewing through long documents.
Now, to make sure those lightning-fast decisions are actually accurate, the model relies on something called a constrained Viterbi procedure. Okay, let's demystify that jargon for a second. Instead of just guessing what a single word is in total isolation, this procedure acts as a global optimization. It evaluates the entire sequence to ensure the boundaries of the sensitive data stay completely stable and coherent. This is absolutely crucial when you're dealing with messy, noisy, unstructured text out in the wild.
Now, what's really interesting about this slide is how the math actually works out for the tagging. The model uses the BIOES format. Begin, inside, outside, end, single. Because it tracks the exact boundaries of a sensitive phrase, the model actually spits out 33 classes per token. Right, that sounds like a lot, but it's just 8 span labels multiplied by the 4 boundary tags, plus 1 background class for all the harmless everyday text.
Section 3. 8 categories of detection. Moving along, rather than just crossing their fingers and hoping the model figures out what counts as sensitive, OpenAI explicitly built a specific taxonomy first and then post-trained the model directly against it. So here are the 8 documented categories. We've got things like account numbers, private addresses, emails, phone numbers, and secrets.
like API keys or passwords. The whole system is engineered to ruthlessly target personal identifiers while trying its absolute best to preserve the harmless context around them. So, for example, it completely removes the specific credit card number, but leaves intact the sentence explaining that a purchase was actually made.
Section 4. Running and fine-tuning. So how do you actually put this into your pipeline today? Well, OpenAI released a slick command line interface tool, simply called OPF. It is beautifully simple and designed so developers can start testing and deploying it right this second.
The operational flow is practically effortless, just 3 steps. First, you install the package locally using Python. By default, it's going to run on your GPU, but you can easily force it to run on a standard CPU just by slapping on the dash device CPU flag. When you fire it up, it automatically pulls the model right down to a local directory on your machine, and boom, you are ready to start redacting or fine-tuning.
Let's move to how this builds into real day-to-day workflows. The OPERF CLI is incredibly flexible. You can point it directly at a standard text file. You can use Unix pipes to string together these complex one-liners for your bash scripts, or, and this is my favorite, if you just run OPERF with no input at all, it drops you into an interactive mode that spits out structured JSON with neat ANSI color-coded previews right there in your terminal. But guys, here is the absolute secret weapon. Fine-tuning is fully supported and deeply documented. The base label policy is static out of the box. But think about it. What counts as PII in healthcare is vastly different from what counts as PII in finance. Because you literally have the weights sitting locally on your machine, you can and absolutely should fine-tune the model to your specific organizational governance requirements using your own labeled datasets.
Section 5. Limitations and real-world risks. Because look, we need an honest reality check here. Even with all this amazing context-aware, machine learning-based detection, this model is not a foolproof magic wand.
So the crucial point is this specific warning read straight from OpenAI's risk section. Privacy Filter is a redaction and data minimization aid, not an anonymization, compliance, or a safety guarantee. Please don't rely on this tool to make blanket anonymization claims to your legal team. It needs to be just one single layer in a much broader, holistic, privacy-by-design approach. OpenAI is actually very transparent about the specific failure modes you need to watch out for. For instance, it can underdetect really uncommon names or simple initials. It might miss API keys if they're formatted in weird, novel ways it hasn't seen during training. Sometimes it even over-redacts, confusing a famous public location with someone's private address. Oh, and its performance definitely drops on non-English text. You absolutely must test this against your specific real-world inputs before pushing anything to production.
As we wrap up, I want to leave you with this final, somewhat provocative thought. We now live in a world where a massive, highly capable model can process 128,000 tokens locally, entirely on your own hardware, in a single pass, totally for free. So what's your excuse for letting PII leak into your training data now? It's time we all level up our data pipelines. Thanks for joining me on this explainer. I highly encourage you to go pull down the OPF CLI and try breaking it on your own data today. See you in the next one.